you, Corbin. Cool. All right, well, let's get started. Thanks so much for joining us, guys. Today we're going to do scaling on the second layer, Lightning Network. So yeah, this presentation is aimed, you don't need to have a technical understanding, but we're trying to give you a technical understanding of how Lightning Network works kind of beyond the scenes. If you're watching online, it's best to watch this if you've already seen parts 1 and 2. You're going to need to have just a basic understanding of Bitcoin scripting to really follow parts of this. But even if you haven't, you should be able to follow along pretty well. But yeah, let's get into it. My name is Gibney. I'm customer support lead at Blockstream. And here's what we're going to talk about today. So there's going to be roughly 5 parts to the presentation today. We're going to talk about the problems, why we need Lightning Network in the first place. We're going to look at payment channels, the basic building blocks of the Lightning Network. We're going to look at the network itself, how you link payment channels together and route payments. We're going to look at present challenges we have with it. And then finally, we're going to get a taste of, I'll basically give you guys a rapid fire look at a bunch of different developments happening to improve Lightning Network and address some of the challenges. Also, if you have any questions at any point, feel free to type them into the chat if you're online right now. And I'll pause from time to time to see if there's any questions. So don't be shy. Let's get into it. So first, scaling up and payment settlement. So as you should know from last presentation, or just if you understand Bitcoin, when you want new transactions to get added, someone needs to find a block. So let's say Alice finds a block and she says, we're going to include all these new transactions in that block. She broadcasts this to everybody else. Everyone checks to make sure all the transactions are okay. And if they are, then everybody agrees, it gets added to Bitcoin's history, and that new batch of transactions are confirmed to the network. So just to look at one example, if we're looking at this transaction here, might send, Bitcoin ownership from this party to this party. And that's how things work with regular Bitcoin transactions. There are some constraints that come with this style, this broadcast network. So this isn't a big deal if there's a small number of users. If you have 100 people using Bitcoin, they can all check each other's activity, not a big issue. Once you have 1 million users using it, it's becomes a bit more of a problem, because now if we want people to run nodes and to check what's going on in the network, each new user adds to the network exponentially. So you have this issue of, basically in a nutshell, broadcast networks scale really badly. And you need to be able to check other transactions cheaply. This is what keeps the system open and decentralized and censorship resistant. So a drawback here is we've had to limit the block space to make sure that people can afford to validate. And that means fewer transactions can happen, and it means higher fees for people who want their transactions included when the network is busy. So at present, it's something around 7 transactions per second. It can vary a bit, but that's roughly what the network can handle at the moment, which isn't a lot compared to, something like Visa can, handle 50,000 transactions a second at peak load, or, probably even more at this point. So yeah, how do we scale Bitcoin is a big question here. And we're going to look at Lightning's approach to doing that. Lightning also addresses a couple other issues, not just scalability, but there are delays in Bitcoin transactions. You need to get them confirmed in a block, and blocks, only come every 10 minutes on average. You also need to wait for several confirmations to make sure that your transaction really is final. So you're usually waiting at least, half an hour or an hour for a transaction to go through. And there's also this issue of unpredictability. New blocks are found every 10 minutes on average. So that means you might get several in a minute, or you might be, waiting a few hours for another block. And Lightning Network tries to get around this. So how do we fix this? We basically need a way to aggregate transactions. That is, if we can make a lot of transactions and add them together and then stick those on the blockchain in a single transaction, this is going to allow us to save a lot of block space and have more transactions. And we need some way to do this with guaranteed block inclusion. So let's say you make some sort of transaction. Even if you can't get it confirmed or included in a block right away, if you can be sure that you can have it confirmed later on, that gives you some similar levels of confidence to actually getting it confirmed. So Lightning Network basically tries to use both of these insights to allows us to scale up. So let's look at the building blocks, which are basically payment channels. Lightning Network consists of a whole bunch of payment channels working together. So we're going to take a peek at how these work at the scripting level. So this is one of the most complicated things we're going to talk about in this series, the next part. So just try and bear with me. If you get a bit stuck with it, just ask some questions, and yeah, we'll go through this slowly. So first, we're going to talk about unidirectional channels. So these are a lot more basic and easy to understand. Unidirectional channel is what it sounds like. It basically allows one person to send another person transactions, and it only goes one way. So let's say Alice and Bob want to open up a channel with each other. Alice might have 100 Bitcoins in her end, Bob might have 0. And Alice can send Bob 10 Bitcoin, and then they update the channel to reflect that amount. Now Alice has 90 Bitcoins, Bob has 10. Then Alice sends another 20 Bitcoin to Bob. And she can continue doing this until there's no money left in Alice's end of the channel. And at that point, the channel is no longer useful because it's only a one-way channel. Alice can't send any more. Bob can't send any to Alice because it doesn't go both ways. But this works. This basically allows you to, there were 5 transactions sent across this channel. And you didn't need them we didn't need to include each of those in a block. So let's look at how you would build a very, very basic unidirectional channel. So you start with what's called a funding transaction. So since Alice is putting up all the money into this channel, she funds the input right here. And we get this output that have 2 different spend conditions. We looked at some of these in Bitcoin problem number 2. So now we can see these in action. So there are 2 ways that this 100 Bitcoins can be claimed. The first way is if both Alice and Bob provide a signature, a 2 of 2 multisig, or Alice can sign for it herself after 1 week has passed. That's what the 1 week time block is. So Alice creates this transaction and she broadcasts it. So this gets included on a block, and now we can say that the channel is open and Alice has 100 Bitcoins in her end of the channel. Now, when Alice wants to send Bob a transaction, what she does is she creates a spending transaction for the funding transaction. So she creates this transaction. Now, she doesn't broadcast it yet to the network, but she creates this transaction that requires both of their signatures and will send Alice 80 of Bitcoins back and Bob 20 of the Bitcoins back. Now, they don't broadcast this to the network because that would close the channel already. But Alice provides this transaction to Bob and she signs it. Now, Bob is holding this. So he knows that whenever he wants to, he can sign it, broadcast to the network, and claim his 20 Bitcoin. So for him, he's confident Alice has sent in 20 Bitcoins. Now, he doesn't broadcast this yet because he wants to keep the channel open. So let's say Alice wants to send another, let's say 30 Bitcoin to Bob. She can create another version of this commitment transaction that sends them both 50 Bitcoins. And so if you look, at the bottom here, that's the same as her sending him 30 Bitcoin. So Bob holds this new version of the commitment transaction that Alice has signed. Bob's happy, he's received his payment, and he's sure he can claim his money when he wants to. And they can continue doing this. So Alice just continually sends an updated version of the commitment transaction. She sends him another 25, she sends him another 25. And once it's finished, Bob can happily broadcast this to the network and claim his funds. And once he's broadcasted it, this alternate spend condition is no longer useful for Alice because the money's already been claimed. This output has been spent. And so what's happened here is the rest of the network just sees these 2 transactions. We have this transaction opening the channel, this transaction closing it, but 5 transactions happened there. Alice sent Bob 5 separate payments. So yeah, we've achieved some minor scaling here. Instead of using 5 transactions on blockchain, we've only used 2. Let's say Bob disappears. What happens if he, goes offline or dies or something? Alice isn't too worried about this because there's always this alternate spend condition. If he disappears for a full week, then what she can do is she can just claim all of her money back. So Bob is strongly incentivized to stay online and stay active. And no one needs to worry about the money disappearing. Now, the time block also means there's another constraint here, that the channel can only stay open for 1 week. Bob is going to need to, close his end of the channel within a week. Otherwise, Alice can claim the money. And you could, of course, set it to a longer time lock, but that's just the example we used here. Right, how's everybody doing? Is that any questions so far? We're good. All right, let's keep it up. So yeah, as we discussed, there's some limitations. They can only be sent one way. Channel has a limited lifetime, and one of the basic things is that you have to close and reopen a channel to add or remove funds. One thing with regular Bitcoin transactions, you can send as much as you want in as large or small a quantity as you like, and the other person can receive it. Within payment channels, you can only send or receive the funds that are locked in the channel already. And unfortunately, 2 of these have already been completely solved. So now we're going to take a look at bidirectional channels. Those are exactly as they sound. Alice can send Bob 10 Bitcoins, and Bob can send Alice 20 of them back. Now, these require a little bit more of a complicated setup. So let's take a look at them. Right, and even though they're bidirectional, if you've run out of money and you're into the channel, you still can't send anymore. Bob sends Alice some, then Alice has more liquidity to send back, but yeah. So let's look at a funding channel. So let's imagine they are both opening a channel, and they're both going to put 50 Bitcoins in their end. Now, they don't want to broadcast this one yet, because as you can see, the spend condition here is just a simple 2 of 2 multi-sig. That means they both need to provide a transaction or a signature to spend this money. Now, you don't want to broadcast this yet, because if you're Alice, you might be worried about Bob disappearing. And if he disappears, then this money is just stuck indefinitely. So they create this funding transaction, but neither of them are going to provide a signature for it just yet. Alice isn't going to give Bob a signed version of the transaction yet. So what they do is they need to create a commitment transaction so they're both comfortable that they can get their money back eventually if the other person disappears. So a commitment transaction in Lightning looks something like this today. So Bob will create a transaction like this that requires a signature from Alice and Bob, and sends Alice her money back, and sends Bob his money back, but with a 1-week time lock, and if Alice knows Bob's secret. Now, hopefully you guys know what hashing is, because that's where this secret mechanism comes in, but we're going to do a very, very quick overview of that. Before we get back to it, so just if anyone's new to this, a hash is just you put some sort of input into this function and you get an output that looks like a random number. And, no matter what the input is, the output is the same length. If you change, a tiny bit of data, so you spell Bitcoin or Bitcoin, then you get a completely different output. So what this means is you can create a script that says, if you want to spend this money, you need to provide the input that produces this output. Now, there's no way to calculate the input of a hash if you just know the output. So this is how this secret spending condition is created. So what this means is if Alice, Bob can claim this 50 Bitcoin if he knows the input for Alice's output that she puts there using a hash function. Now, they each create this version of the commitment transaction, and so they both know that as long as Alice hasn't told Bob her secret, she's okay with someone broadcasting this transaction, because she just needs to wait 1 week and she gets her money back. And they each hold a different version of this. So Bob will hold the same version, but with his money stuck in a time lock that Alice can claim if she knows his secret. So now, here's just a visualization of that. If someone knows a secret, they can claim the output, and the other spend condition is no longer valid. So once they both have this version of the commitment transaction, they both feel secure, they both can sign this transaction and broadcast it. And once this gets confirmed on the blockchain, they have an open channel. They have a channel where they both have 50 Bitcoins in it that they can send to and from each other. All right, how are we doing? Do we have any questions so far? Or are we doing all right? Everything's corn. You're right, Paul. All right. Oh, someone's typing. Right. Yeah. Now, normally we'd wait to the end of a section to ask for questions, but I know this this part of the presentation is a bit complicated, so I want to make sure everybody's on the same page before we move on. So you can wait. Okay, sure. We'll do that at the end then. Okay, cool. All right, so let's keep going. All right. So both parties know they can get their money back within a week if the other person, disappears or tries anything shady. So they have, they provided this funding transaction on the network, and the channel is open. So now let's say Alice wants to send Bob 10 Bitcoins. So what she does is she sends him an updated version. So this is the commitment transaction that Bob holds. Alice can send him a new version of this. Now, if you look, this is what's going to change. These are going to change from 50s to 60/40. So that means Alice is sending Bob 10 more Bitcoins through the channel. And the other thing she's going to do is she's going to reveal, on her version of the transaction, she's going to reveal her secret. So what that does is invalidates an earlier commitment transaction. So whenever you're sending a transaction on a payment channel, you're basically updating this commitment transaction to reflect a new set of balances for each party. And you're revealing secrets from the previous commitment transaction. So what happens is if you reveal your secret, that means the other person could claim all the money. And that's your way of guaranteeing you're not going to broadcast an earlier state to the channel and claim the funds for yourself. That is, when Alice sends Bob 10 Bitcoins so that he has this 60/40 output, he needs some way of knowing Alice isn't going to close the channel and add 50/50 as it was before. That's where the secrets come in. So when you're making a payment on Lightning Network, you're updating the commitment transaction, and you're providing your previous secret to invalidate an earlier commitment transaction. And that's basically how payments are made across Lightning. Now, the important thing here is that this stuff isn't seen by the rest of the network. This is all just unbroadcasted states. These are things that each party, keeps so that they're sure no one else can cheat them, and then they can go back and forth and do as much as they like. Then let's say Bob wants to send her some money, he can send 20 back to her, and then the amount gets switched. So the cool thing about this is you get to send tons of transactions back and forth to and from each other. You only need 2 transactions in total on confirmed in a block. And in the majority of scenarios, the players will likely cooperate to close the channel. The funding transactions that we've seen with those complicated spending conditions, those are basically assurances. Those are a way to make sure that the other party doesn't reverse transactions. But when they actually want to close, they can just create a simple transaction like this. Let's say they agree that this channel has outlived its usefulness, and the sum of all the transactions leaves Alice with 25 and Bob with 75. They can create this simple closure transaction. They both sign it. The money goes back to them, and they're both happy. And this is the only stuff that needs to be confirmed in blocks. So this is a way you can get lots and lots of transactions within only 2 transactions. So I'll double check for questions before we move on to linking nodes and routing payments. Looks like we're okay. Yeah, we have one. What do you say when you say no one else on the network can see the transactions? Right. Okay, so I should be clear with my language. When I say transactions, I'm talking about there are Lightning transactions, and then there are on-chain Bitcoin transactions. So what you see here, these are the 2 on-chain transactions that need to get confirmed on the blockchain, need to be included in a block. A transaction on Lightning Network are basically the 2 parties exchanging updated versions of these commitment transactions. These don't get broadcasted to the network. These are held by each party just to make sure the other party doesn't cheat and try to, revert to an earlier state of the channel. So all of these, commitment transactions, these are exchanged back and forth, and you can think of them like an insurance policy, just to make sure that the other party doesn't cheat. But you never actually need to. You very rarely need to broadcast them to the network. As long as both parties stay online and are cooperative until the end of the channel, You just need to broadcast these two things: this transaction on the left to open the channel, and this transaction on the right to close it. Worst case scenario, one party tries to cheat or disappears, then you might need to broadcast one of these commitment transactions. But again, most of the activity is not needed to be seen by the rest of the network. I hope that answers the question. Cool. Oh, hang on. All right. You're asking if those transactions might be broadcast to the wider Lightning Network. No, actually, right now we're just talking about transactions between two parties. No one else, not even the other people on the Lightning Network, need to know about these. We haven't gotten to routing yet, which is going to involve payments through other parties. We're going to get to that in the next section. But for now, we're just talking about payments between Alice and Bob, and no one else needs to know about them. Only Alice and Bob need to be communicating with each other. All right, any other questions before we move on? One more question coming. Are off-chain transactions stored in the node itself, the individual node? Yes, the Lightning node. So when you're operating a Lightning network, you're going to need to be running a Bitcoin node, and you'll run a Lightning node on top of that, and then you're going to need to store the previous commitment transactions, because each one requires a slightly different secret to reveal. And you need to keep a record of earlier commitment transactions and the earlier secrets, so that if anyone tries to broadcast an earlier one, you can claim it. That's not ideal, but again, that's going to be fixed in a future update, which we'll be talking about later in the presentation. But yeah, each individual, under this model that I'm describing right now, each party would need to keep track of previous commitment transactions. All right, if that's it, we're going to move on to the next part, linking nodes and routing payments. All right, so I'm going to talk about a thing called node hopping. One of the constraints here is the payments I was describing there, the Lightning payments, are just between two different parties. They're between Alice and Bob. Now, let's say that Alice wants to pay Carol or something. She would either have to open up a channel directly with Carol, or she would need a way to pay money through her payment to Bob. So this is a way that you don't need to directly have a channel open with someone in order to pay them. You can pay through other parties. So there's some advantages here. Their fees are collected by intermediate nodes that provide routing. A difference between on-chain transactions and Lightning payments are that on-chain transactions are based on the size of transaction, so not the quantity of Bitcoins involved, but how much space it takes up the blockchain, whereas the main constraint in Lightning Network is liquidity, so cost is based on the quantity of Bitcoins you're sending. And another bonus is that this provides incentive for running nodes. It's minor, but it's there, and we get this much more efficient use of block space. So let's look at how this happens. So Alice has a channel connected with Bob, and Bob has a channel connected with Carol. And Alice wants to pay Carol, let's say, 25 Bitcoins. So we need a way that Alice can send Bob 25 Bitcoins, and Bob can send it to Carol. Then they all update their channel balance accordingly. Now, some of you might spot a problem with this, in that, let's say, Alice wants to send the 25 to Bob. Bob's supposed to send 25 to Carol, but what if he just decides, I'm going to keep this for myself? Carol doesn't get her payment, and Bob steals 25 Bitcoins from Alice. So we need some way to prevent this from happening. And we use a similar mechanism used in the committed transactions, we use hashed secrets, as we did before. So what happens is if Alice wants to send a payment to Carol, Carol comes up with some sort of secret input and provides the output to Alice. So when Alice is sending Bob this payment, this Lightning payment, he can only claim it if he reveals some secret, Z. And actually, Alice or Bob, they don't know what that secret is. Only Carol knows. She provided the output to Alice. So now, when Bob creates his channel, his transaction routing the fees to Carol, he locks it by the same secret, Z, but let's say with a 2-day time lock instead of a 3-day time lock. So what this means is if he doesn't claim, if neither of these parties claim the payment within 3 days, will revert back. The 2 days will revert back. So once they kind of put forth these payments, Carol can reveal her secret Z and claim her funds from Bob. And once that happens, Bob will know the secret Z, so he can claim his funds sent to Alice. Now, the time lock is really important here because you need to make sure this expires before this transaction. Because if this were to expire first, if this was like a 1-day time lock, Carol could wait until that happens, then Bob might have a risk of being out of money. So as long as the expiry of the payments further down the line happens sooner than earlier than the earlier ones, then everybody could be guaranteed that as long as they stay online or operating properly, either all the payments go through or none of them. Alice can be sure her payment will reach Carol. Carol can be sure she's gotten it, and Bob doesn't have to worry, because if Carol ever claims this money, he knows he'll be able to claim this money. And so, yeah, that's basically how you make a payment through another party. All right, any questions with that one? No? So it's all about how hash secrets and time locks interact. That's the core of ensuring transactions are legit. Yeah, basically, like there are three components. There are three scripting components that go into Lightning channels. There's multi-signature, there are time locks, and pre-hashes, we call them. And yeah, using those three primitives, you can build up the whole Lightning network from that. And again, why would Bob do this? We're not showing this here because we don't want the numbers get too complicated, but he would actually be able to collect a small fee. So, maybe Alice sends him, 50.001 Bitcoin, and then Bob sends 50 Bitcoin to Carol. To 25 Bitcoin to Carol. Also, I'm using really big numbers here because round numbers are easy to work with. You would not be, we don't send people 25 Bitcoin in a Lightning channel. This is still an experimental network. It's generally better for small payments, but yeah. And Bob, it doesn't really cost him much to provide the service. I mean, if he's running a Lightning node anyways, if he has these channels open, it basically costs him a little bit of bandwidth, and he needs to, make sure his channels are well funded. All right, so we're going to take a little bit of a bigger picture look at this. So let's simplify this. The individuals are kind of the white dots, and the channels are the blue lines. So you could repeat this process across many nodes. Like there's no reason that you couldn't do this, across 4, 5, 6, 7 nodes. So this allows you to route payments much, much further away. The thinking to make sure is that each node must have the funds already in place. So what that means is, let's say we had this state of the network where Bob had 0 funds and hit the end of his channel to Carol. If Alice wanted to send, any money to Carol, she couldn't go through this route because Bob doesn't have the funds to send to Carol. So yeah, we can just visualize that as a red dot at the end of one of the channels just means that that end of the channel is empty. So in this situation, you couldn't route the payment because you've got this single point in the chain without liquidity. So in that case, that payment wouldn't go through. Further ones couldn't. You would have to find some different route. All right. All right. If no one's got any questions, then we'll move on to existing challenges. So some of these you might have been able to guess at. There are a lot of constraints here. These are just a few of them I'm listing. And so the first one has to do with the punishment scheme. So we saw earlier that the incentive for people not to cheat is that if they cheat, the other party will be able to basically take all the funds from the channel. That's great that we're encouraging people not to cheat, but there are issues with this. For example, software isn't perfect. There have been cases where someone has accidentally broadcasted an earlier state and the other party's automatically claimed all the funds. That's not ideal. So we need That's something that can be improved upon. Routing grows more challenging with growth. So the larger the network gets, requires work so that we can route payments more easily. There's something called the Titanic scenario, with people are kind of worried about. Not sure if it's a great name, but we'll talk about that. The base has to do with rising fees. We're still going to need a lot of block space for this. This is not a panacea. Some people, we don't want to oversell this. Like there are still going to be a lot of constraints with how many channels can open, because they do need to open and close at times. And then there are some micro liquidity challenges. What happens when you run out of funds in one network or in one channel? You need to keep these. You need to keep your Lightning nodes online, which isn't ideal. That's a hot wallet, and we need ways to improve the end user experience. Let's look at these a little bit more in depth. As we said earlier, if someone tries to cheat and send an early transaction, someone can claim all the funds. Liquidity, let's say there are no funds in this part of the channel, you can't send that way. Maybe you find another route, but it might not be available. One thing that can help with this liquidity problem is if you have, let's say, E and F routing payments from A to B. If a bunch of these payments happen, you might end up with all the funds at this end of the channel. But if the network can be structured in such a way such that D is sending C funds, this will help keep this central channel balanced. So there are a variety of ways that you can try and increase liquidity and keep things going. So another thing you could imagine, for example, is let's say there's an individual and a merchant. So let's say I'm going to my local coffee shop and I open a channel because I want to be buying coffees there. And maybe that merchant is, has a larger channel with my place of work or something. I can pay the merchant a lot for my coffees over the month, and then, maybe the merchant buys supplies from the place I work, and then the employer would send me, payment through this. If you have some sort of loop like this, it really, really helps the channels stay open, because they'll rebalance themselves if funds are going both ways. The Titanic scenario, which people have talked about, this is a little bit outdated. I remember people talked about this a lot a few years ago, but people were worried about this scenario where fees get really, really high. I've shown here, this is a graph of Bitcoin fees from back in 2017, 2018. When it was just very, very expensive to send transactions in Bitcoin. So there's a lot of activity happening in the network. Because of Lightning Network's punishment scheme using time locks, you might get in this scenario where someone broadcasts a transaction and fees are too high, so it doesn't get confirmed, and then it can be very, very hard to claim your funds back. So we need some way to deal with that. For the original Lightning Network white paper, this is back in, I think, 2015 or so. It states that Bitcoin will be able to support about 35 million users at current block size, assuming these transactions level, size of transactions, blah blah blah. They're saying that we would still need an increase in the block size to support everyone. So we're going to take a look at that in a bit. And then, the smaller challenges in UX, and the shorter, medium term, how do you reveal challenges? Even though I showed examples of how that could be done, it's easy to show an example of that in an ideal scenario. How's it going to look in the real world? You have this issue of on-chain transactions allow you to receive as much as you want at a time. As long as you have a Bitcoin wallet, someone can send you as much as you like. Whereas if you're receiving a Lightning payment, you need to have a channel open with funds being ready to send to you. It might be, a bit of a pain for a newcomer to receive Bitcoin, open a channel, and then just receive a Lightning transaction. And then when you're managing multiple channels of liquidity, that can be cumbersome. We need a way to make that simpler for people to use. So now we're going to take a look at some upcoming improvements. Does anyone have any questions about the previous section? Still with us? All right, we have one question coming in. Okay, the Bitcoin off-chain wallet is not the same as the Lightning wallet channel, correct? My understanding is you must fund a channel with your Lightning network and can't fund a channel with your on-chain wallet, even if the on-chain wallet is associated with your... I'm not 100% sure I understand the question. Your Lightning network, you'll need to run a Lightning node on top of your Bitcoin node, and yeah, I think I might ask Daniel to answer this one. He probably knows it a bit better than I do. Like yeah, okay. So your Lightning node is going to have its own on-chain wallet, and you send funds to that first. Okay, these questions are getting a little bit out of scope of this presentation. I'll let Daniel answer if he can, but I'm gonna move on with the presentation before we get back to that. Could that be the same wallet associated? I think in theory it can, Corbin, but I don't think it's how it works at the moment. Yeah. Keep in mind, guys, this presentation is not aimed for like kind of practical everyday usage, like how it works in the implementations we're using today. We're just trying to get a higher level look at like how it works. But yeah. Okay, so let's take a look at some upcoming improvements. We just discussed a few issues and challenges that Lightning Network has. So let's look at what we're going to be doing about it. So here's a brief overlook. We're going to talk about Watchtowers. They're a way to outsource enforcement of the channel state. We're going to look at L2, just a way of replacing punishments with a different mechanism. We're going to talk about multi-party channels, which are they're exactly what they sound like. We'll get into it. There's some on-chain protocol developments coming up that really help us out with space efficiency. We're going to talk about splitting roots, and if you have time, maybe atomic swaps and cross-chain compatibility. So Watchtowers. One of the challenges with punishments is that you need to stay online. You need to keep your Lightning Network node online, because if you go offline and another person tries to cheat and broadcast an earlier state, you need to be able to claim those funds back. Maybe people don't want to have their node consistently online, or maybe get a power outage and they go out or something. Watchtowers are a way that you can outsource this. So you can basically, for a fee, pay another service to keep an eye on the network and claim funds back for it if someone tries to cheat. So the way this would work is, let's say that Bob has, deviously broadcasted this earlier state, and Alice is supposed to receive, 50 of the Bitcoins instead of 40. And if Alice knows the secret, Bob's secret, because he should have given it to her, which she received a payment that changed the balance. What she can do is she can provide this transaction to the Watchtower and say, hey, if I have the wrong amounts here, this should be 100, or this is correct. And she can create this transaction and give it to the Watchtower and say, hey, I'm going to go offline for a while. If you see this transaction show up on the blockchain, please broadcast this. What this means is that, the Watchtower would get 1 Bitcoin and Alice would get the other 59 back. And that way, even if Alice, goes offline for a while, she can be pretty confident that, Bob's not going to cheat, because the Watchtower will get the money back for her. Watchtower is happy to do this service because if anything happens, Watchtower gets some of Bob's money. And as long as, the Watchtower is someone who's going to be online scanning the blockchain anyways, not an issue for him. All right, look at L2. Now this is a way to replace punishments. So we don't really have time to get into the nitty-gritty of how this works, but essentially this is a way that instead of allowing someone to claim all of the funds in a channel if someone tries to cheat, it's a mechanism that just allows you to revert to the correct channel state. The reason that we don't have this yet is because it does require another protocol development to happen still. We need a new signature type. I believe it's tentatively called SigHash no input, which would be a way to claim to spend to sign for a transaction regardless of what the input is. But this provides a few advantages. First of all, the punishment transactions, you might run into this issue where fees go way up, and since you've already created the transaction to claim the funds back, you might get locked out. Whereas L2 allows you to set fees for these transactions when you broadcast them. And again, even if there's an accidental broadcast of an earlier state under a system using L2, you wouldn't claim all the funds. You would just correct that to the proper current state. So hopefully in the next year or two, we'll see that go live. But yeah, we're going to need to wait until Bitcoin soft forks in this extra signature type. Multi-party channels. This is one of my favorite parts of Lightning Network to learn about. So far, we've only been discussing two-party channels. That is, you got two players sending money back and forth to each other. But there's no reason you can't do this with 3 parties or 4 or 5, etc. So the same constraints apply, but they work a little bit, but they're a bit better or worse depending on which ones you're looking at. So, for example, all parties must be online to send and receive payments. Now, if you have 3 parties in a channel, it's more likely that one of them will be offline. So that's a bit more of a drawback. As with regular channels, you can't add or remove funds without channel closure, and it's also limited by the size of multi-signature, which is at 15. So let's take a look at how these would work. Let's say Alice, Bob, and Carol all open a channel together with 50 Bitcoins each. Alice can send 20 Bitcoins to Bob, and Bob can send 40 Bitcoins to Carol, and they can continue doing this to and from each other as long as they are all online. We can take this a step further with a thing called channel factories. There's a paper released on this called Scalable Funding of Bitcoin Micropayment Channel Networks, which is a bit of a mouthful, but these have become known as channel factories. And what they are Bitcoin Lightning Network channels within larger multi-party channels. So what this does is it allows Bob, Alice, and Carol to create one large multi-party channel. So this kind of light blue circular barrier shows like a single large channel between Bob, Alice, and Carol. And they each put 50, Alice and Bob put in 50 Bitcoins and Carol puts in 90. And then they each open separate channels with each other within it. Now, what this means is that, let's say Carol goes offline for a little bit, Alice and Bob still send their funds back and forth. If Bob goes offline, Alice and Carol can send their money back and forth. If they are all online, they are free to open and close these bidirectional channels with each other. And again, none of this needs to hit the blockchain. You just need a single large transaction to open the multi-party channel. And then everything that happens within there doesn't need to be broadcast to the Bitcoin network. So it gives you some extra flexibility there. And what does everyone else see? They would just see something like this. If they each fund their end of the channel 50, 50, 90, then the funding transaction would have a single output, needs to be signed by all 3 parties. And then they can do as many transactions as they like within there. And at the end, all 3 of them sign it and they each get, whatever funds are left for them. And yeah, again, the bonus here is that you can have more flexible use. There are more parties you can send to. You can aggregate even more transactions. The challenge being the more people are involved in a channel, the more likely one of them will be offline. But this does offer us more flexibility. I don't believe these are used live in Bitcoin yet, but they're just yet another thing that are being worked on. Now, last thing we're going to talk about is some protocol developments coming up. Several of these recently got assigned bit numbers, so they're kind of on the horizon. So they're Schnorr signatures. This is a way of combining many signatures into one. So you can basically, add up signatures 1, 2, and 3 into a single signature. So this means space saving for multi-signature transactions. Then there's something called MAST. It's Merkleized Abstract Syntax Trees. Now this is a way to store more complicated Bitcoin scripts in a Merkle tree. So it only reveals the parts that get used. We're going to look at that on the next page. And then Taproot essentially combines Schnorr signatures and MAST and gets you even more privacy and scalability with them. So the way those work is, right now, if you have this output and you're using a pay-to-script hash, which is how it's mostly used in Bitcoin right now, you just take all spend conditions together, you hash them together, and that's what goes in here. And then when you want to spend it, you reveal the script, and then you fulfill one of the script conditions. So everybody gets to see what all the options were. Using master taproot, you hash each different spend condition separately, and then you hash those together. So I've circled here what gets revealed as Bitcoin works right now. Once we get this working, you'd only need to reveal, the root hash, these two hashes, and the 1 week time lock. And so this never needs to get broadcast. This gives extra scalability, and it gives extra privacy. And you can do this for more and more complicated scripts. So if you have like a channel factory that has, several different layers of spend conditions that need to be fulfilled, you can just sort of hide all that and only reveal what gets signed for at the end. So now this gets you even better, even better efficiency, because if we think of our multi-party channel example earlier, if we aggregate the signatures together, this would only look like a single address and a single signature. Earlier you could probably guess that it was a Lightning channel being open and closed. This you wouldn't even know. Like for an onlooker running a node, this might be just a simple transaction to someone, then sending to other people. We talked earlier about block space. Actually, I'll see if anyone had any questions about that. Nope, we're okay. All right, we talked earlier about the concern expressed in the original white paper about block space needed. But I've underlined something here. I've underlined assuming 2,000 transactions per megabyte or 500 bytes per transaction. We don't actually, that assumption is obsolete now. Since we've had segregated witness added, we've had a block size increase, and we can actually fit many more transactions within, the same block space. Once we add Taproot and get Schnorr signatures going, this will allow transactions to be even smaller. So, as time goes on, we're able to fit more and more transactions in the same amount of block space. That doesn't mean this is entirely solved. There still will be constraints, but it's good to see a lot of progress has been made in the last 5 years. Another thing we can talk about are multi-path routing. So we talked earlier about if let's say you want to send 30 Bitcoins, this person wants to send the person on the right 30 Bitcoin, they can't go through this route because there's only 10 Bitcoin in that end of the channel. They can't go through, this route because there's only 20 Bitcoin there. Multipath routing is a way where you can split the payment into two pieces, but still have them both confirm, and use two different routes. So this is a way to just help with liquidity issues. So that's another thing being worked on. There's actually like a tremendous amount going on in the Lightning Network space. So I just really constrained by how much stuff I can fit in here. But there's still some open problems. Other than those, Lightning channels are in hot wallets. That is, they need to remain online. That's not ideal for security. We, almost all of the exchange hacks, for example, you hear about are from hot wallets. Cold storage is much, much safer. So that's a challenge. There are ways that people talk about like cooling them down somewhat. You can get these this middle ground between being completely offline and but still a challenge. User experience is a big issue. Like what we've explained today, ideally in the future when people are using Lightning Network, they will need to understand all that. They should be able to just send funds regularly, and it'll just say it's been sent. We don't want people having to actively manage channels. But that's going to take a lot of work. We're going to need a lot of work with UI and basically abstracting that out. And how can we hide all that from the user? There's one last thing I want to talk about. I mentioned before that once you have funds locked into a channel, you can't add or remove them. You have to close a channel and reopen it. There's a technique called splicing in or splicing out. What this essentially means is it's a way that you can kind of close and reopen a channel in a single transaction and add funds to it. So here you could, Bob could add 65 Bitcoins to the channel. So basically they, both sign for the channel, which has 100 funds in it, 100 Bitcoin. Bob signs an extra input adding 65, and now he's added 65 Bitcoins to his channel. And then you could also do the opposite, of course. You could, create a transaction, send some out. These do, of course, require on-chain transactions, but they're slightly more efficient than completely closing, completely reopening a channel. So yeah, I know there was a lot I threw at you guys at the end there, but it's hopefully will whet your appetite into looking into these things a little bit more. So as always, don't trust, verify, and thank you very much for tuning in. And then, yeah, if you have any more questions, stick around and ask them. Okay. You implied earlier that anyone would be able to tell that transactions broadcast to the blockchain related to network activity. Okay, yeah, maybe I didn't mean to imply that you would know for sure. It's like, yeah, with any chain analysis techniques, it's generally heuristics. You would just guess that's the case, but it's not necessarily so. I mean, there probably are some, other use cases of 2-of-2 multi-sig transactions. It's not necessarily true that they would know for sure, but people could guess at it. Right now, if you see transactions that have like 1 or 2 inputs, a 2-of-2 multi-sig, and then spending that to 2 different outputs, you wouldn't know for sure that's a Lightning Network channel being open and closed, but you can guess it is. By using Taproot and, like not even Taproot, just like by using signature aggregation with Schnorr signatures, it can look indistinguishable from, a transaction being sent to a single party and then sending it to other people. So it's not guaranteed, but it's just an extra layer of, it just makes everything look even more similar. That's one of the advantages. From a UX advantage perspective, I guess one big channel is going to be able to understand why they need to commit funds initially to start operating. Yeah, absolutely. Like there are a lot of I kind of glossed over it quickly at the end because I mean there's so much I could make like a bunch of presentations about these, but yeah, absolutely. The UI and UX itself is a big hurdle we still got to overcome. One of the interesting things about splice in and splice out is that it kind of allows you to have a single wallet that, when needed, can send an on-chain transaction or a Lightning Network transaction. So let's say you want to receive a transaction from someone and you don't have any, liquidity, let's say you want to send a Lightning payment to someone and they just can't receive it because they don't have any incoming channels. You could use splice out to send them an on-chain transaction from a channel of yours. But yeah, that stuff's all in development at the moment. You have one more point you're unsure of? What factors determine when channels must be open and closed? Yeah, that's a good question. I mean, from a strictly technical level, like they can be open indefinitely. Likely, you'll see things like, maybe you have, maybe the other player wants their funds back. Maybe you have, $50 in Lightning channel, and you don't think you're going to use Lightning for a bit and you want to send it to someone else, you would probably close the channel. Or, maybe you believe that opening a channel with a different person would get you a better connection, so routing is, more easily done. You might close it and reopen it. There are a variety of reasons. It's kind of hard to say at the moment. From a strictly technical level, they don't need to be. You probably would want to occasionally close and reopen them as well to save space, because with the punishment mechanism, now L2 is going to kind of fix this, but at the moment, the more payments you make within a single channel, the more commitment transactions you need and secrets you need to keep track of. So if I make hundreds and hundreds of payments off of a single channel, that's going to require more and more data to be stored by my node. So once in a while, yeah, you might want to close and reopen just to kind of reset everything. But yeah, with L2, actually, that shouldn't be a concern. You can just keep the most recent channel state. All right. So if no one's got any questions, that's it. Thank you very much for coming, and thanks for your kind words, Corvin. And yeah, I will be back in a week or two. We're going to be talking about fungibility and privacy. Is going to be our next presentation. So we'll be talking about things like CoinJoin and confidential transactions and chain analysis heuristics. And so yeah, I hope to see you there. Thanks for tuning in, guys. Bye-bye.